Hello everyone, this is Dr. Lennon, and today we're going to take a look at the net change theorem and average value. So this is one of the PowerPoints from the text, and essentially we learned last time from the fundamental theorem of calculus and antiderivatives that the integral gave us a way to find the net area between the curve and the x-axis. And that area is given by computing the antiderivative and then subtracting the limit values. So that's what we see in the first line there on the integral from a to b of f of x. You can figure that out by finding an antiderivative, plugging in b, and then plugging in a. Typically, the antiderivative we're going to choose is just the one where the constant value is 0. So how does this talk about net change and average value? Well, average value we can kind of think of as the kind of the net change is just the total change that's going on. So one way that this is different is so this is going to apply when you have something that you're thinking about as a rate of change function. So notice when they're taking the integral here, they're thinking about f prime of x. So if you took the antiderivative of the derivative of something, it would be its own antiderivative. So if you're thinking of this as some net change, something that's behaving like, say, miles per hour, something like velocity is going to act like a net change, as we learned when we studied differentiation. The integral of that velocity would give the total change over that, say, time interval. So if you were driving in a straight line, you know, at some speed or some function that's measuring a speed, that say from, you know, starting time 0 to 1 hour later, and you did the antiderivative over that time interval, what that would give you is that would give you the total distance traveled there. It is a little bit different if you were not traveling in a straight line. Let's say you were going forward and then back, and then you know, the net change would be giving you your net change in position, not the total distance traveled. So for instance, if just to kind of understand the difference here, imagine we had somebody, so the difference between net change and total change. So net change, let's say we have somebody and you start here, and then I don't know, maybe you drive 5 miles, then for whatever reason you drive 2 miles back in this direction, and then from there, you know, you travel another 4 miles. Then your net change in this scenario would be 5 minus 2 plus 4, which is 7. So your starting point here, you would end up 7 miles away from your starting position to your finished position. This would be 7 miles. But let's say the total change would actually be the total distance, or the total distance traveled, let's call it that. Total distance would be different because you actually went farther than 7 miles. In terms of how far that you were driving, you would have gone 5 plus 2 plus 4. You would have gone 11 total miles in this scenario. So that's one difference between when you talk about net change versus total change. So the net change is just measuring where you started to where you finished, and it's not taking into account what happened in the meantime, whereas your total change would just represent that. So a lot of times in the integral picture, you know, it might be something where you have, like, you know, a part of the graph above, if this is the graph of your velocity, and then you have something below, and then you have something else above, where this was 5 and this was 2 and this was 4, something like that. So if you would integrate, say, from, I don't know, if this were 0 and we went out to, I don't know, some distance, or let's just use a and b, and we called this f of x, then if you would integrate this function, or maybe we should do it like they did in the thing, since this is going to be measuring distance, velocity, something like that. The integral is going to measure the distance. So if we called this f prime of x and we integrated f prime of x dx, we would have gotten that net change of 7. If you wanted to get the total change, what you would integrate is you would actually integrate the absolute value. So we'd be integrating from a to b the absolute value of f prime of x, and that would be giving us the total change, which we saw to be 11. So the net change that we saw would be behaving like this integral, and the total change would be behaving like this one, because the integral on its own is going to be a net area, so the parts of the graph that would be below the x-axis would be negative areas, and the parts above would be positive, unless you did something like take the absolute value. Okay, so that's the basic idea. So understanding the basic idea, there's no new mathematical machinery here. If we're trying to find antiderivatives, that's still going to be the same techniques that we learned using those basic rules. So really, there's not too much in this section that's new from a computational perspective. Okay, so the net change theorem can be applied to any rate. It doesn't have to be a velocity. That's just one of the most natural examples. So if you have a rate of growth of a population and you look at some net change of it over two specific time intervals, that's going to tell you the change in population. So that's what's going on here. We've got a bunch of different letters representing things, but we know that this is like a P prime type of thing. And if you're going from T1 to T2, that's just going to tell you how much the population of this area either grew or decreased from time 1 to time 2. So that's what it means from the net change. It could be a positive or negative, as you know, populations could decrease or increase. It could even stay the same potentially. Here's another one, cost. If you have the cost of producing Q units, then this is known as the marginal cost. We'll look at more examples of this in the future when we get to chapter 6, which involves a lot of applications. But anyway, the antiderivative of this would tell you how much. So let's see. It's going to tell us the total cost increase from producing Q1 units to Q2 units. So you might be producing 5,000 units, and then all of a sudden you're producing 6,000 because there's some increase in demand, and this is going to tell you the total change in cost in producing those additional amounts of units. Here's one with volume. So these are just examples where you're kind of figuring out the letters and you're saying, okay, this is change in volume over time. This is going to tell us how much the volume has increased. So pretty straightforward when you're just looking at the variables and trying to figure out what's going on. And then velocity was the one we already talked about. So the net change in position is known as the displacement, whereas we have the total distance traveled, and notice they're taking the absolute value, which is the same thing that we did in the example we just looked at. Okay, and they even gave the same pictorial example I did. So your displacement here would be A1 minus A2 plus A3. That's the displacement, but the distance, when you take the absolute value, this A2 is going to now become a positive quantity because of the absolute value, so you just get A1 plus A2 plus A3. So I did it with some basic numbers. This is just using those A1, A2, and A3s could be any numbers depending on what the graph looks like. Okay, and then acceleration is the rate of change of the velocity, so you could actually perform this net change theorem on something with an acceleration function, and what's going to be happening there is just going to tell you how much the velocity is either going to be increasing or decreasing, right? If you look at maybe something like throwing a projectile where the only force acting on it that you're worried about is gravity, we know that's 9.8 meters per second squared. So each second the velocity is going to be increasing at a downward rate of 9.8 meters per second. So that's a common example too. So we can iterate, we can look at rates of change and keep doing that. And acceleration is going to be the most common of those that we see. Okay, so let's look at one where we have a marginal revenue. So this is a rate of change function, and what they want us to do is we have this marginal revenue here, and we want to figure out, it's telling us to compute this integral from 200 to 300 of r prime of q dq. So what does that mean? That means the q is units, and the revenue is the amount of money taken in from producing that many units. So this will be telling us the total change in revenue from increasing our number of units from 200 to 300. And if you look in the first sentence, it's telling us that the revenue is measured in dollars per unit. So this is going to be dollars. And here's our function 26 minus 0.04q. So in order to do the antiderivative, remember, it's just going to be 26q minus 0.04q squared divided by 2. We're just using the polynomial rules to find the antiderivatives there. So again, we're going to compute the antiderivative. As I mentioned, it'll be 26q minus 0.04, change the q to q squared, and then divide by 2. So 0.04 over 2 is going to be 0.02. So it should look like 26q minus the 0.04 times the q squared over 2. And then remember, with the polynomial, we have to plug in both the limits and subtract. So we're going to want to plug 300 in for both q's, and then subtract with parentheses and plug in the 200 for both q's. So we see that here. And they've, again, divided 0.04 by 0.02, so by 2, which gives 0.02. So we plug in the numbers. Again, remember, when you subtract, really this whole thing's in parentheses, so distributing the negative makes it a minus 26 times 200, and then the negative being distributed will change the negative in the middle to a plus 0.02 times 200 squared. And then from there, you can plug that into your calculator, and you'll get the net change in revenue as a dollar amount. So we see that the net change is $1,600. So the amount of revenue is increased by $1,600 by upping the production from 200 to 300. Okay, so that is the interpretation there. Okay, so the note on units they're probably going to refer to is essentially what we're doing when we're taking the antiderivative, is we're kind of multiplying by the time factor that's changing it. So if you have some quantity like we just did, dollars per unit, then when we take the antiderivative, we're essentially multiplying by the unit of units there, and those are canceling. Or with velocity, it would be something like miles per hour. When you take the antiderivative with respect to time, you're essentially multiplying by the unit of time, and you end up with just miles. That's why we're getting the total distance change. So there we go. As we said, the unit of measurement for this is the product of the unit for f of x and the unit for f of x and the unit for x, because of that differential there. So what happens here, what does the integral represent? Well, we've got the units of a of t, then we're multiplying by the units of t. So a of t here is absorption rate in the bloodstream, which is going to be that mu g stands for micrograms per milliliter per hour. And the units for t are hours. So basically, we're going to be taking micrograms per milliliters per hour and then multiplying by hours. So our final units will just be the micrograms per milliliter. So as you see, we'll probably, we have those multiplied. I thought they'd have it out more, but yeah, it says right here, the integral represents the net change in drug concentration in the patient's bloodstream from the end of the first hour to the end of the third hour. So the final units above, it says micrograms per milliliter, as we anticipated. So kind of, if we want to go back and actually write this down, let's see what's going on in this example. It's not a whole heck of a lot, but we have micrograms per milliliter per hour, and then when we integrate, we're multiplying by hours, so those units cross off and we just get the final units of micrograms per milliliter, and that is the units that we're left with, right? So that's essentially what the integral does. We have some integral of a of t dt. So the units of a of t were the micrograms per milliliter per hour, and the units of time are just hours. So when you integrate, you're multiplying by those hours and they're canceling out. And that's why we get this unit here as our final set of units. Okay, so the other concept in this section we want to talk about is average value. So one thing to think about that I kind of like to reference this by is kind of just almost thinking like a rectangle. What's going on? Well, if we've got some function and we've got some curve like this, this is some f of t or something like that, and we have some time interval a to b. Well, we know from the fundamental theorem that the area, the shaded area here, is the integral from a to b of f of t dt. Now, what if you could somehow morph this into like a perfect rectangle that had the same area? Well, the height is varying over this time interval. So we'd like to know essentially what is the average y value that would turn this into a rectangle. We know if we kept the rectangle, but we wanted to keep the bottom the same, the width of this is b minus a. So if we wanted to make a rectangle with the same area, but this were the average height instead, how would we do it? Well, if this is the whole area, that's all we actually have to do is divide by that bottom width that we know, b minus a, and we should get a height that's average. So that's essentially what the average height theorem says, is the average height of f of t from t equals a to t equals b is given by the integral divided by b minus a. So that's kind of it. So if you kind of think of the area kind of as a rubber sheet, and you could morph it but keep the bottom the same, you're kind of taking this weird looking object and making it something look regular. That way you can determine what the average height along that interval is going to be. So that's how I think about it in my brain when I think about this average height concept. So as we see right there, the average value is just the integral that we're talking about over that interval divided by the length of that interval. So something like this, find the average value of the function 1 plus x squared on negative 1 to 2. So why don't we do that down here. So let's say we have the this example. We want to find the average height of f of x equals 1 plus x squared on the interval negative 1 to 2. Okay, so I mean, you could think about the picture if you want. We know 1 plus x squared is just the parabola that's, you know, moving, that's shifted up 1. It looks the same shape as y equals x squared. And, you know, we're between these two values here. So this is kind of the part of the graph that we're looking at. So the average height, they were just calling this f average. Well, it would be 1 over b, which is 2, minus negative 1. That's the length of our interval. And then we multiply by the integral from negative 1 to 2 of our function, which in this case is 1 plus x squared dx. So this comes out to 1 over 3. And then we have our antiderivative. Antiderivative of 1 is x, and x squared would be x cubed over 3 from negative 1 to 2. And then we want to evaluate that integral. So it's going to be 1/3, and then plug in the 2 first. So 2 plus 2 cubed, which is 8 over 3. And then we need to subtract negative 1 plus negative 1 cubed over 3. So let's do the arithmetic here. We have 1/3, and then 2 plus 8/3. Well, 2 is 6 over 3. So this would add up to 14 over 3. And then we're subtracting, well, we've got negative 1 minus 1/3. So we're subtracting negative 4/3. So what we have is really 1/3 times 18/3. And 1/3 of 18 is 6. So this looks like it comes out to exactly 2, right? 18 over 9 is 2. As long as I didn't botch up the arithmetic anywhere, which I don't think I did. Okay, so that would tell us, okay, the average height of this basically, notice the interval on the bottom is 3. This would have the same area as a rectangular box with a width of 3 and a height of 2, right? So that irregularly shaped shaded area would have the same area as the rectangle with a width of 3 and an average height of 2. So that's kind of the way I think about it. So let's go back to the PowerPoint and double check that they got the same answer that we did. Yeah, so they got 2 exactly as well. So that looks like it is it for the PowerPoint slideshow here, I think, for this section. So 2 relatively simple concepts So I'll come back in another video where we work again on some more concrete examples using some of the word problems and some other functions to try and determine some net changes and some average values. But really no new mathematical machinery. We're just applying the concepts that we learned from the fundamental theorem of calculus and looking at some other graphical observations and how that can relate to applications. So this is Dr. Lennon signing off.